Kia ora, welcome to video 4 in the series Insightful Integration. In this video, we're going to look at a differential equation, a fairly standard one to be honest, except the answer to the problem requires us to find the coordinates of stationary points. So it's kind of a scholarship question where multiple standards of work are combined. I guess when you're doing NCA, integration on its own is separate to differentiation, and scholarship, the stuff can come together. So it's a pretty reasonable question. If I was rating on a scale of 1 to 5, all the best, and we'll catch you after the intro music for the solution.
Okay, the first thing to realise here is that the differential equation is separable. It looks like a mess, but if I separate by moving the 4, or just the y cubed plus 1 actually will go underneath there, and the dx up the top, then things become quite nice. We're integrating 3y squared all over y cubed plus 1, and on the right hand side we're integrating cos squared x with respect to x. I've lost my 4. Okay. So the left hand side is a fraction. The fraction doesn't algebraically simplify because there's 2 things in the denominator and 1 thing in the numerator. If you don't notice it, you could make the substitution y cubed plus 1. And if we do that, the derivative of it appears at the top. So if you didn't notice that, that's the way you would go about it, making a substitution. But this is one of those special f dash over f types, f dash over f, which has got its own integral formula. Whenever you see the denominator's derivative appear at the top, or some factor of it, then the integral will be just the log of the denominator. So we've got log of y cubed plus 1. We need a plus c somewhere. And then on the right hand side, to integrate 4 cos squared x, we need to use a trig identity for that. We can't write it as cos cubed over 3, okay? If you're thinking cos cubed x over 3 or some variety of that, it just doesn't work like that. When we turn cos squared x into something that we can integrate, just have a look at your formula sheet to verify this, but 4 cos squared x is equal to 2 cos 2x plus 2. And so we can replace this right hand side integral by integrating 2 cos 2x plus 2, and then that's something I can integrate. 2 cos 2x, just anti-diffs to sine 2x, and then the 2 anti-diffs to 2x, and then we'll put a plus c on eventually. Okay, what are we trying to achieve here? Because we've just found the expression for the curve that satisfies the differential equation. We're looking for the 2 stationary points. So stationary points are where dy dx equals 0. So if I go back to this problem, I've already got dy dx, this bit here. If I make that equal to 0, then I'm solving one of these 2 factors here has to equal 0. Okay, so either y cubed plus 1 equals 0, which won't be the case, because if you look at the picture that's been given to you, the y values are always positive, and so y cubed plus 1 will not be 0, and therefore it must be cos squared x being equal to 0. So we've got cos squared x equals 0 at stationary point, where dy dx equals 0. And if we solve this equation, cos squared x equals 0 has it tells you that cos x must equal 0, and that's got heaps of values for x, but the first 2 that we want are x equals pi over 2 and 3 pi over 2. Okay, because if we look at the graph, the stationary points we're finding are the first one there, which is pi over 2, and the second one, which will have to be 3 pi over 2. Kind of matches up there because 3 pi over 2 is triple pi over 2. Alrighty, so if we substitute those x values in to this expression here, which is our implicit solution, we will get the y values of the stationary points, However, we do need to find the plus c as well. Going back to the original problem, f of 0 is equal to 2. I haven't used that information yet. So when x equals 0, y is equal to 2. And if I sub that in, I get log of 2 cubed 8 plus 1 is 9. Log of 9. Don't need the absolute value symbols because 9 is positive. X equals 0 into the other stuff. Sine of 0 is 0. 2 times 0 is 0. So it's just c. c is ln 9. So we end up with ln y cubed plus 1. I don't need the absolute value symbol 0 over because we're dealing with positive y values. Equals sine 2x plus 2x plus ln 9. And then we just need to sub in the 2x values into that equation and rearrange them. And when you do that, x equals pi over 2 gives a y value. You can write it in exact form if you want, but it's about 5.9180. And the 3 pi over 2 gives you a y value of 48.1344. I'll leave you to check those. Hopefully you found that video not so bad. The problem itself, the differential equation, looked tricky, but it was a separable one. There's only a few types of differential equation that you can ask in NCEA, and there was no hint there, so it had to be one of those. And then the sneaky part of this problem was finding the stationary points meant that we needed to use the dy dx equals 0 information, and it's easier to use that in the original differential equation up here where I just made dy dx equals 0. It's easier to do it that way than it is to go to our expression here and differentiate it to find the dy dx again, because we'll just get back to where we started anyways.